We have now looked at biasing of a transistor at a given drain current quite in detail for both PMOS and NMOS, and we have seen that the feedback can be completed in various ways. In this lesson, we'll look at some more alternatives to this. Of course, there is no end to this. The way you complete the feedback around a transistor, there is an endless variety, but we will take a few of them for illustration. And actually, these circuits will be useful not just for biasing. It turns out that if you apply inputs at the appropriate places and take the outputs at the appropriate places, you will also have useful functionality. Okay. So first let me consider drain feedback biasing. Okay, what do? We have a transistor, let me call it M1. We connect a current source I0 to the drain, and we have to complete the feedback with some positive incremental gain to the gate, from the drain to the gate. Now what is a circuit that we know which has a positive incremental gain? There are many circuits. Certainly the common drain amplifier or the source follower, that's an example. And the common gate amplifier is also another example. Okay, so let's take the common drain amplifier or the source follower. Okay, now I have this part and I want to complete the feedback using a source follower. So let me do that. Let's say the source follower is biased at a current I1. Then as far as the source follower is concerned, that is the input and this is the output, and the incremental gain is almost 1. So I can complete the feedback like this. Okay. So many times you see composite structures like this using two transistors, but you shouldn't get confused. This is the source follower and it's completing the drain feedback around this transistor. Now you can also apply signals to various places and it will have some functionalities that you can see in the examples and the assignment. Okay. So let me call this M1 and this will be M2. Okay. Now we can take another example where we sense at the drain and feedback to the source. In this case, what do? The gate is tied to some fixed voltage VG0. This is I0. Because the sense of variation we want at the source is opposite to what we get at the drain, we have to complete the feedback through a negative incremental gain. Okay. Let me take another example of sense at the source and feedback to the gate. Okay. In this case, to sense at the source, we have a current source. Let me call it I2 just to distinguish between things. The drain is connected to the supply voltage, and because the sense of variation we want at the gate is opposite to what we see at the source, we have to complete the feedback through a negative incremental gain. Again, let's try some possibilities for this negative incremental gain. What possibilities do we have? One obvious thing is the common source amplifier. The very first amplifier that we discussed, it has a negative incremental gain. So let me use a common source amplifier in this place. Okay, so that's a common source amplifier and I complete the feedback that way. Let me call this I3. Okay, and maybe I'll call this mx and my. Okay, so how did we come about this circuit? We wanted to bias mx at a current I2. We complete the feedback to the gate through a negative incremental gain, which is a common source amplifier using my. Now if you look at these two circuits, they're actually exactly the same. Okay, so if you make this correspondence, M1 is the same as My in the other case, and M2 is the same as Mx in the other case. I0 serves the function of I3 here, and I2 is I1. Okay. Don't worry about the values, but you see that the topology here is exactly the same as the topology over there. Okay. So in this case, we think of this transistor being biased using drain feedback. We feedback from drain to the gate. In this, we think of biasing this transistor by feedback from source to the gate. Okay. So either point of view is perfectly valid. Okay. Once you have a feedback loop, all components in the feedback loop have feedback around them. Okay. You can choose any one transistor and say the other transistor is helping to complete the feedback loop. So this was just to illustrate to you also that you can think of the circuit in different ways, but arrive at the same circuit. Okay. And let's take a couple of more examples. Let's say we sense at the drain and feedback to the source. Because the sense of variation we need at the source is opposite to what we have at the drain, we have to complete the feedback using a negative incremental gain. Okay. And what could I use for a negative incremental gain? I could use a common source amplifier, and this time, just for fun, let me use a PMOS common source amplifier. A PMOS common source amplifier is this, and I complete the feedback loop that way. Okay. So this coloring makes it obvious. This is completing the feedback loop around that transistor. Let me call this M1 and this one M2. Okay. So there is a huge number of variants, and in every circuit you can swap NMOS for PMOS and so on. Okay. So this is another example, and in every case it's not important that you know every topology beforehand. Once you are given a topology, you should understand what it is doing. First of all, you should be able to recognize this feedback. You should be able to see that there is feedback from drain of M1 to the source of M1. Okay. Or if you think of M2 as the central actor, then you can see that there is feedback from drain of M2 to the gate of M2 through this. And what is this? This is a common gate amplifier. Okay. So you can think of feedback around M1 provided by M2. Okay. Feedback around M1 meaning from drain to source, and M2 is a common source amplifier. And the same circuit can be equally well thought of as feedback around M2 meaning from drain to gate provided by M1, which is a common gate amplifier. Okay. So both points are equally valid. Now what is also important is you should be able to put down the incremental picture of these things, or if some other bells and whistles are added to these circuits, including those components, and analyze. I mean, normally you will have some input and some output, and you may be asked to calculate the transfer function or maybe the input resistance somewhere and so on. All these things you can see in the examples. Okay.